Hi, in this video I'm going to continue on the topic chemical equilibrium, and here we will be talking about how the temperature change affects the equilibrium as well as how the catalyst affects the equilibrium. After that, we will also talk about some industrial consideration when it comes to equilibrium. So let's get started. Now first of all, temperature affects an equilibrium system in three ways. First of all, it is the time required to attain equilibrium. Now you know that in general, when temperature increases, reaction occurs faster. And also remember that it takes time to reach equilibrium. So we say that when temperature increases, both forward reaction and backward reaction occurs faster. Therefore, it takes a shorter time to reach equilibrium. So underline, higher temperature, forward and backward reaction occur at a faster rate. So it requires less time to attain equilibrium. Okay? Now, the second one, about the equilibrium position. Now, first of all, refresh your memory. We have exothermic reaction and endothermic reaction. Exothermic reaction is a reaction that releases heat. Endothermic reaction absorbs heat. Now think about it. If the surrounding temperature increases, then the system wants to counteract the increase in surrounding temperature. Basically, it wants the surrounding temperature to decrease. Now, in order to decrease the surrounding temperature, a system can absorb extra heat from the surrounding. Now, if you want to absorb extra heat, basically, you are doing more endothermic reaction. So, if the forward reaction is an endothermic reaction, then it may as well perform more forward endothermic reaction. In this way, it can absorb more heat from the surrounding and therefore decrease the surrounding temperature. So this is how we make use of the Leschetiz's principle to predict how the equilibrium position will shift when there is a temperature change. Right? So let's have a look at the sentence here. Now, first of all, if the forward reaction, in this case exothermic, then the backward reaction will be endothermic and same magnitude of energy change. The magnitude of delta H would be the same. So if this is negative 100 kilojoule for forward reaction, the backward reaction would be positive 100 kilojoule per mole. Now, if the reversible reaction, which the forward reaction is exothermic, right? When the temperature increases, the system will respond by shifting the equilibrium to the left. Now, shifting to the left will basically do more backward endothermic reaction. In this case, it will absorb more heat from the surrounding and therefore lowers the temperature, therefore counteracting the increase in surrounding temperature. Okay? So that's the idea. You can also jot down the case if the temperature decreases. Okay? So you think about it. When the temperature decreases, okay, then basically you shift to the right. Shift to the right. Now shifting to the right hand side, it will result in a net forward exothermic reaction. As a result, more heat is released to surrounding and therefore causing the temperature increase. And this one is basically counteracting the decrease in temperature. So that's the idea. Okay? Now, but pay attention to one thing. If you go back to this example as written from the statement here, when temperature increases, then there would be a net backward reaction. So you may think that the backward reaction goes faster, the forward reaction gets slower. But bear in mind, since overall speaking, the temperature has increased, so the forward and backward reaction both speed up. But we say that the backward reaction speed up to a greater extent than the forward reaction. So at the end, we will have a net backward reaction. Okay? So, bear in mind that as long as temperature increases, the reaction goes faster. Similar idea goes for the one that I just drew. Okay? When temperature decreases, we say that the equilibrium will shift to the right, provided that the forward reaction is exothermic. Now, you may think that when you shift to the right-hand side, that means the forward reaction rates go faster than before. But pay attention to how you describe or how you present the ideas. Now, first of all, when temperature decreases, both forward and backward reaction should be slower. Bear in mind of that. But we say that the forward reaction becomes slower to a lesser extent than the backward reaction. Therefore, there will be a net forward reaction. That's why we will say that the equilibrium position shift to the right, leading to a net forward reaction. And therefore, there will be a net exothermic forward reaction, releasing more heat and therefore heating up the surrounding. Okay? So pay extra attention to how temperature change will actually affect the reaction. There are three of them. Time to attain equilibrium, it has to do with the rate of reaction. And here, equilibrium position will also has to do with the rate of reaction. So be extra careful as to how you present your explanation or description. Okay? Now, down here, for equilibrium constant, Kc, so this time Kc does change because temperature changes, right? Now, how can you predict the Kc changes? Now, we will predict it using the Kc expression. Now, Kc expression, again, it is basically the product concentration at equilibrium over reactant concentration at equilibrium. Okay? So, think about it. If we have an exothermic reaction down here, an increase in temperature, like I said, will result in a leftward shift. So it shifts to the left. Okay? Now think about it. If you shift to the left, that means you will have more reactant, less product. Okay? So when you have more reactant, less product, how does it affect Kc? Well, of course, the Kc will be smaller because you have a smaller numerator and a larger denominator. So the Kc over here will therefore decreases. Okay? So this is how we determine the Kc changes upon a temperature change. Okay? So on the other hand, again, I will illustrate to you another example. Again, we make use of this exothermic reversible reaction. Let's just say this time we have a temperature decrease. Okay? So temperature decrease, of course, the shuttle principle wants the temperature to increase, so it will shift the equilibrium to the right-hand side. So shift to right. Now shifting to the right, that means you will have a net forward reaction. So when you have a net forward reaction, that means you have more product, less reactant. Therefore, Kc will become larger. Okay, so this is how you predict, okay, the Kc changes when there is a temperature change. Okay. Now, so three effects that you have to consider when there's a temperature change. Okay, the time required to reach equilibrium, the equilibrium position, and also Kc. Now, this diagram basically illustrating all three changes. So you see, First of all, R becomes P, and this is an exothermic reaction. So the blue one showing you the 25 degrees Celsius, and when temperature increases, this is how the curve changes. Now the first thing you need to pay attention to is that the first thing you have to pay attention to is the time it takes to reach equilibrium. Originally, here, okay, so this is time to reach EQM. Now, when temperature increases, you notice that now time to reach equilibrium is shorter, okay? So it takes a shorter time to reach equilibrium. This is the first thing you have to pay attention to, okay? And the second thing is you have to look into the equilibrium concentration of the chemical species. So you see, for reactant, the reactant concentration increases, the product concentration decreases, right? So here, reactant concentration increases, the product concentration decreases, okay? So that is hinting towards a shifting of equilibrium position to the left-hand side, okay? So there's a leftward shift, okay? There's a leftward shift, okay? Now, from the reactant and the product concentration changes, you can also conclude that the Kc will decrease. Okay, Kc will decrease because you have fewer products and more reactants. So Kc decreases. So three effects are shown in this single diagram. And make sure you know how to interpret, and maybe next time you are asked to sketch a new curve based on a change in temperature. Okay? Now on the right hand side, there is a practice question, very simple, and I want you to pause the video, spend some time to finish it off, and then quickly check the answers. Okay, let's have a look. First of all, this one is an endothermic reaction. When temperature increases, then it takes shorter time to reach equilibrium, so the time to reach equilibrium will decrease. Now, when the temperature increases, of course, the system wants the temperature to decrease, so it wants to perform more endothermic reaction to absorb extra heat. In this case, it will definitely shift to the right. And shifting to the right, meaning that you got more product and less reactant, so the Kc increases. Now, the third one here, we have an exothermic reaction. Now, all we know is the equilibrium position shift to the left. Shifting to the left, that means you have more reactant and less product. So more reactant and less product, meaning that the Kc will decrease. Okay? Now, if you shift to the left, knowing that the forward reaction is exothermic, meaning that the backward reaction is endothermic. So what makes a system to do more endothermic reaction? Probably because the outside is very hot, so you want to absorb extra heat from the surrounding. So perhaps temperature has increased it, okay? So when temperature has increased it, the time to reach equilibrium will also decrease, okay? Now, down here, this time we know that when temperature increases, Kc increases. Now, when Kc increases, that means you have more product, less reactant. When you have more product, less reactant, that means the equilibrium should shift to the right-hand side. So shift to the right. Okay, when temperature increases, it will shift to the right. So that means to the right-hand side, the forward reaction should be endothermic, right? So here should be endothermic, right? Because think about it, when the temperature increases, the system wants the temperature decrease, so it wants to absorb extra heat. So you basically want to do more endothermic reaction. And to do more endothermic reaction, it will shift to the right, basically meaning that the forward reaction is endothermic. Now, lastly, when temperature increases, the time to reach equilibrium, of course, decreases. Okay? So that's the idea. Okay, next page. Effect of catalyst on equilibrium. Now, a catalyst, remember, first of all, the definition. A catalyst is a substance that can alter. That means change. But most of the time, we are increasing the rate. Alters the rate of reaction without itself undergoing permanent chemical change. Okay? Now, for reversible reaction, a positive catalyst speed up, right? And it does not only speed up the forward reaction, but it also speed up the backward reaction. Okay? And most importantly, it speed up both reactions to the same extent. Okay? Therefore, the only changes to the equilibrium is that it takes a shorter time to attain equilibrium. Okay? For equilibrium position, it does not change because the concentration of the composition doesn't change and there's no temperature changes. Okay? Kc also doesn't change because the temperature remains constant. Okay? So if you look at this graph, if you have catalyst, the only changes is that it reached equilibrium at an earlier time. And of course, the curve will be having a steeper initial slope. Okay? Alright, so that would be the effect of catalyst on equilibrium. Now, down here are some industrial considerations. Now think about it. When it comes to industry, okay, you are like the boss of an industry, all you are concerning is about money. And when it comes to money, not only the cost itself, but you also consider about the production of goods, right? Of course, the ideal situation is that you can produce a lot of goods very quickly at very low cost. And most importantly, you want to keep your employee safe. You want to keep your working environment safe. So actually, these are what a boss of an industry will have to consider about. So here, the rate of production, yield. Yield has to do with the number of goods or the amount of goods, costs, and also safety. Okay. Now, these criteria, however, contradict one another. Like, think about it. If you have to cut costs, probably the manufacturing process will be slower. Probably you're getting a lower percentage yield, and probably the environmental situation is more compromising. So you see one often contradict one another. Okay, so that's why a manufacturer need to make compromise. Okay, they want to consider all the factors and they choose the most optimum, the best combination of the four. Okay, now let's look at this example. Now this one is called Haber process, and this is used to make ammonia, and the reaction is nitrogen reacting with hydrogen to form ammonia gas, and the forward reaction is exothermic. You need to memorize this. Now, considering all four factors, all four criteria, if you want to speed up the reaction, rate of manufacturing process, if you want to speed it up, of course, you want to go for high temperature and high pressure. Okay, high temperature, particles are moving at higher speed, higher collision frequency, right? Pressure, again, basically increasing the concentration, therefore having a higher frequency of collision. Okay, but you increase the temperature will drive the equilibrium to the left. Knowing that the forward reaction is exothermic, when you increase the temperature, it will shift the equilibrium to the left. Okay, that will lowering the yield. Okay. Also, if you have such a high temperature and high pressure, the maintenance of conditions would be very expensive and at the same time very dangerous. Okay, so this is how one criteria contradicts the others. Okay, now if you want to increase the yield, if you want to have more percentage yield, then you want to go for a lower temperature. But a lower temperature is not desirable because the reaction will be proceeding too slow. Okay, so what are the industrial compromise? So down here, the optimal temperature and pressure, the best situation is that the reaction taking place at 450 degrees Celsius at 200 atm. Okay, this is the best choices of conditions. We use ion catalyst to speed up the reaction. Now, using catalyst is always good, provided that it is not super toxic. All right, number 3 here, we say that the hydrogen and nitrogen feedstock are continuously pumped into the reaction vessel, and at the same time, ammonia are removed. So here, the idea is we keep a high concentration of nitrogen and hydrogen, so high concentration of the reactant, and ammonia, we keep removing the ammonia. So basically, the system is always not at equilibrium, because we keep changing the reactant concentration and product concentration. But we do so because we keep making the equilibrium favoring the forward reaction. Okay? Because we take away the ammonia, so the product concentration decreases, you keep pumping in the nitrogen and hydrogen, so you keep increasing the reactant concentration. So the equilibrium will keep shifting to the right, favoring the production of products. Okay? So these are some methods to increase the yield. Okay? And number 4 here, unreactive feedstock is recycled back to the reaction vessel to reduce waste and to avoid contamination. Okay, this may not have to do with the rate of reaction or the yield, but it may have to do with the cost or even the safety. Knowing that hydrogen gas is extremely flammable, if you simply discard it, that could be problematic. All right. Now, on next page, we have a practice question. So, spend some time working on this practice question, and we will check it. All right, let's have a look. The key reaction during contact process. Now, contact process is a process involved in making sulfuric acid. It was in a certificate level syllabus, but now it is not. Now, basically, sulfur dioxide reacts with oxygen reversibly to form sulfur trioxide, and it is an exothermic reaction. How temperature and pressure affect the production rate and yield. Now, if you notice, temperature, pressure, rate, yield. So there are basically 4 questions. How temperature affects the rate, how temperature affects the yield, how pressure affects the rate, how pressure affects the yield. Okay? Now, of course, you will present your ideas in sentence, but for me, I will do a table. Okay? I will have temperature, pressure, how does it affect the rate, and the yield. Okay? So first of all, temperature, how does it affect the rate? Of course, the rate increases because, okay, the average Ke of molecules increases, therefore collide more frequently with greater energy. Okay? So of course, most importantly, the frequency of effective collision increases. Okay? Now pressure, of course, rate increases. Okay? Simply because the collision frequency increases. So again, the frequency of effective collision increases. Okay? So these are the rate consideration. Now as to the yield, so increasing the temperature will actually decrease the yield. Yield decreases. This is because, okay, the equilibrium position will shift to right. So there will be a net backward reaction. Okay? Now, what about pressure? Now, increasing the pressure will actually increase the yield. Okay. Now, here it doesn't talk about how mean temperature, pressure, but so we can say now if temperature increases, if pressure increases. Okay, you choose one side. Okay, you don't have to do both side account. So here, the yield will increase when the pressure increases because there are fewer gaseous molecule on product side. So equilibrium position shift to the right. Okay? So that's the idea. Part B. In addition to deploying an optimal temperature and pressure, suggest two other ways to enhance the manufacturing process. So we just talked about it. You can talk about use a catalyst to speed up the reaction. You can also recycle unused feedstock. Okay, to reduce waste, or you can talk about constantly removing the product in order to favors the forward reaction. Okay, so these are possible answers. Alright, so that's it for the video.